So here we're looking at a methane with carbon 1 up, carbon 2 to the left, carbon 3 in the back, and carbon 4. And so if we were to orient carbon 3 to the back, we would see it goes from 1 to 4 to 2 in the clockwise direction. Now let's continue to sort of walk to the left, except there's a wall there and we can't walk through it. So you can still see 3 is in the back. Now let's begin to move ourselves so that we can put 4 away from us. Once carbon 4 is away from us, we now have 1, 2, it's hard to see the 2, but that's towards us, and then 3. So going clockwise, it's 1 to 2 to 3, when 4 is in the back. And now we can go back to our original position. Now let's orient 2 away from us. So we continue to move to the right, walking around the molecule. Now 2 is in the back. And what you can see is number 1, number 3, and number 4 are towards us, and that's the orientation in the clockwise direction, 1 to 3 to 4. Now, in order to get 1 behind us, we have to lift the molecule up into the air. And now that we've done that, 1 is behind us. So looking at 4, 3, and 2, if we were going to go in a clockwise direction, it would go 2 to 4 to 3, or 4 to 3 to 2, or 3 to 2 to 4. So for the way the molecule was sitting on the ground, we have to lift it up in order to orient number 1 away from us. So that completes that exercise on orienting the methane molecule with the 4 different groups, each one sequentially away from us. Now let's do that for a Fischer projection. So in this Fischer projection, the green and red are pointing towards you, and the white and yellow are pointing away from you. So let's walk up to the molecule, and what we can do is predict the clockwise orientation of groups if the white is away from us, and that would be red going to yellow, going to green. If the yellow ball was away from us, we would be going from white to red to green. Now, if we would like to look at the red oriented away from us, we're going to need to walk around the molecule like so. And now you can see that the white, the green, and the yellow are in the clockwise orientation. Now we have to continue to walk around the molecule to get the green behind us, and when we do that, it's white to yellow to red in the clockwise rotation. We're now actually behind the molecule, and now we can go back to our original forward position. So orienting the 2 vertical positions which are away from us with a Fischer projection is relatively straightforward. If we want to orient the 2 positions towards us, that means we have to walk behind the molecule. We'll do that one more time. Here the red is now behind us. So it goes white, green to yellow. Go back to our original position. Now let's orient the green behind us. So we'll go behind the molecule to the right. And now the green is behind us so that it goes from white to yellow to red. Okay. And back to our original position. Now let's look at the cis diequatorial 1,2 dimethyl cyclohexane. So first we're going to rotate the cyclohexane. The two red atoms are the methyl groups. So we'll have to walk up to the molecule to take a better look at it. You can see that both of the reds are the axial or the equatorial. Let's rotate. And you can see that both of the methyl groups are equatorial. Now, do you see any evidence of this molecule being unstable as we rotate around? Do you see any deformed bonds? And if so, then that would make the molecule indicate that the molecule might not be stable. Okay, so this is trans 1,2 dimethyl. Now here is the diaxial trans 1,2 dimethyl cyclohexane. And you can see that both of the methyl groups are now in which positions? They're in the axial positions. Now, do you see any evidence here that the molecule is unstable? And actually you do, because the methyl groups are not straight up and down in the axial positions. They're actually being pushed away, or they are pushing away from the two hydrogens that are diaxial in the 1,3 relative positions. So for trans 1,2 dimethyl cyclohexane, this conformation is less stable. And as we back out, you can see again the bonds, that bond is pushed back. Okay, let's take a look at just a regular cyclohexane molecule, and let's do some ring flipping. We'll walk up to the molecule so we can grab one of the carbons. Notice carbon 9 and 10. What's the position of 9? What's the position of 10? Now let's make the molecule flat. Is this a stable conformation? Why not? You can still see that for hydrogen 9 and hydrogen 10, that 9 is still above the ring, 10 is below the ring, 8 is above the ring, 7 is below the ring. So now what we'd like to do is we'd like to grab C4 and let's finish the ring flip. So for carbons 9 and 10, how did they end up? They started 9 axial, 10 equatorial, and at the end of the ring flip, we'll do this one more time. 9 is axial, 10 is equatorial. We'll do the entire ring flip, and now 9 is equatorial and 10 is axial. And that happens for every single one of the hydrogens. They reverse their positions from being axial to equatorial, but notice none of them loses their position relative to the ring. If they were above the ring, they stay above the ring. If they were below the ring, they stay below the ring. Hey, here is an SN transition state. Which one? We have a bromine coming in and displacing a chloride. And as the bromine gets closer, what happens to the hydrogens? And we can go over here and look. The bromine, the carbon, and the green chlorine are all in the same line. This is the transition state. Now as the bromine gets closer, the chlorine gets farther away, and what happens to the hydrogens? Okay. Here's just some big molecules that we're able to put into virtual reality. This is cholesterol. we've got a 6-membered ring that I'm pointing out the laser. There's another 6-membered ring. If I want to rotate this around, you can see there's another 6-membered ring right there. So there's 3 6-membered rings that are fused together. And then there should also be a 5-membered ring. So cholesterol is a steroid. It has a 6, 6, and 6, 3 6-membered rings, 5-membered rings, and then that long hydrophobic tail. There's a single polar atom at the top, which is the OH, which I'm not pointing at right now. It's at the top of the molecule. So now let's see if we can bring this down without toppling it on ourselves. There it goes. Perfect. So now we can start looking at the ring fusions. For the first 2 rings here, and there's an OH group right there with the oxygen red. Looking at these ring fusions, this is a carbon-carbon double bond. And you can kind of see that from the 1 hydrogen. If we look at the other ring fusion, what we're going to see is that the carbon-carbon fusion is actually trans, because the 2 hydrogens are diaxial. So you can kind of see there's a methyl group that's axial, there's a hydrogen that's axial, so the fusion point to the 5-membered ring is trans as well. We can try and walk around the molecule a little bit and go over towards where the oxygen is. But notice we can get a very good view of what the shape of this cholesterol molecule is. And how would you describe that cholesterol molecule as having what kind of shape? And I would call it a rod. I would call it rod-shaped. So cholesterol is made up of fused ring systems, which we can really look at well in the VR. Now we'll go to the biggest molecule that we've put into VR so far, and that is a chunk of DNA. So the nitrogens are blue, oxygens are red, phosphorus is yellow, and so this is a piece of double helix. It's kind of hard to see, so we'll have to take a little bit of a walk around this molecule. So we'll go to the left here. Let's go to the left. And now you can begin to see the base pairing and the places where molecules can intercalate within the base pairs. So you can kind of see that to the left, or sorry, to the right. We can continue to walk, and you can again begin to see the spaces between the base pairs. And you can kind of see the double helix if you follow the red and yellow side chains. So then it's kind of hard to get this down to ground level, so we'll have to submerge part of it. Because now we can take a look at the base pairing. So once we're there, we can go ahead and walk over and walk into the middle of the DNA. So we'll kind of go over here, and we get really close here. That oxygen and that hydrogen are hydrogen bonded. That hydrogen and that nitrogen are hydrogen bonded. And that oxygen, and there's a hydrogen on the other side of the nitrogen that's hydrogen bonded. So we're standing right in the middle of the hydrogen bonding pair in the center of the DNA, double helix. There's a hydrogen bonding pair. There's another hydrogen bonding pair with that nitrogen. And so we can get a really good view of the base pairs being flat that allow them to hydrogen bond very strongly, which is what they do in DNA. You can see a little bit more of the double helix here. So that's kind of our demo in terms of what we've done with the virtual reality system. We're going to be doing more and hopefully implementing this into next year's organic class as we begin to talk about shapes and function and maybe even modeling some reactions within the virtual reality.